future scientific directions. So let me get started introducing some what I call a stepping stone. That's the fourth paradigm of material science.
Claudia, yeah? I'm sorry. We see your presenter's view, so
okay.
So I just wanted to say it's fine,
well,
of course.
Let me go back. I stopped sharing because I try again. It has to do with the fact that I'm using two screens, a dual screen. Does it work now?
Yes.
Looks perfect.
Okay, great. Looks better. So then let me try getting into it. As I said, data might sound a bit dry, but I would like to convince you that it's just all about materials. And what we are all doing is trying to find better materials, because I think our future needs them very, very hardly, depending whatever you look at. And we want, of course, to make progress. So if we have something that is hard and tough, we want to have a hammer that is harder and tougher. Or we would like to have materials that are lightweight but still ductile, such that finally you can transport with less energy. We would like to have things that are small, so miniaturization is quite an issue, but things should also be flexible. So if you have a closer look here, then you will see that this cell phone is a little bit curved, such that it fits into your pocket. We also would like to have non-toxic, sustainable materials. And so this is quite a few years old now. I always like this example because this was the first edible transistor. Right? So it's all built of components that are not only non-toxic but also edible. So maybe in the future, if you don't like your cell phone anymore, you will be able to just eat it. I don't know if it tastes you. Energy is a very important aspect of our society. So we would like to save energy in terms of also lighting and all kinds of energy harvesting like things. Well, the question is, of course, what is our role? What's our goal there? The role of theory, as we know it, was always to provide more insight. So it would complement experiments, but also to provide, having this insight from this equation that you can analyze, to also provide more understanding of what, for instance, is measured in various experiments. So in order to proceed and actually get you to the actual topic of my today's presentation, I would first like to take you a little bit back in history. And a little bit not only means a little bit, but it means something like 4,000 years. And this is the time, the Middle Ages, where experiments were born, so to say, when people started to experiment with different materials. And then it took actually quite a long time, so until, let's say, around 1600, so not 4,000, but 400 years ago, when theoretical science or theoretical physics was established. And this started with the laws of classical mechanics, electrodynamics, and now, of course, what we have here is the laws of quantum mechanics, which form our daily basis of research. So, but since then, well, the computers came into play, and having faster and faster computers, this allowed us not only to solve, let's say, the problem of a few materials, but to apply, for instance, quantum mechanics, but of course also classical physics, to a lot of different problems that we can solve numerically on the computer. And this is what established our third paradigm of research, which is computational science. And the methods, of course, you all know them. It's Monte Carlo simulation, molecular dynamics, and in particular density functional theory and methodology beyond. So why do we call this a third paradigm, a different one? Because, well, you can do more. You can than just what you can do with paper and pen, because we can also perform what we call computer experiments. So in that sense, we're somehow in between these two, or let's say we can complement with the third paradigm the other two. And this is actually our basis for our common research, of our daily research nowadays. When talking about history, I just want to get back to 100 years ago and introduce Max Planck, the founder of quantum mechanics, actually, to and what he was thinking about what we probably are doing right now. He always said that the only truth is experiment, and or the only means of extracting knowledge, and everything else, and in particular theory, he called this poetry or imagination. So I'm really happy to be a poet, but yeah, I will come back to this and discuss a little bit what this means, being a poet. So what do we do in our daily research? And in particular, what do we want? I mean, being a theoretician and also computational material science means if you really want to go for the goal to help improving or finding new materials even, we need to have methodology that treats all the materials on the same footing. So we need to have very well established theories, which I think we pretty much have. They're further developed, of course. And then to understand and also predict all kinds of properties from the structure, the response to light, magnetic properties, so whatever you can think of, mechanical properties. So we need tools in hand that allow us to predict the properties of various materials on the same footing. And this brings me to, let's say, the topic maybe every one of us, or nearly every one of us, is concerned with, and this is density functional theory and also methodology beyond. So DFT tells us that density is the key variable. And why do we love it so much? Simply because we can treat now all different kinds of materials indeed on the same footing. So talking about atoms, molecules, clusters, spike materials, surfaces, interfaces, nanostructures, you name it, right? So we can treat everything with one and the same equation. So in that sense, we have the methodology in hand, and also, of course, methodologies that going beyond that. The question is, what can we do with it, and how can we exploit it maximally? So DFT is the workhorse of computational material science. So, and this also tells us what our daily research is about. So what is physics today? And I take the example of course, of our own research of theory, but I think it's not so much different if you look into other areas of research. And so let me take my, let's say, introduce my group to you, right? So this is Nora and this Archana, and these are the many people, or let's say part of the group. And if you see, obviously some of these people, they work with methodology, with paper and pen, like this. Nora, for instance, she has implemented quasi-particle self-consistency in GW. So you need to do derivations with paper and pen, you implement something, so that she doesn't need or didn't need much of computer power, right? But there are others, they can run calculation on a single machine or on a computer cluster, or some of them even need high performance computer centers in order to run the calculation. Now, I'll come back to this, what this means in terms of data, but first I like to ask the question, how we work scientifically. And I would like to exemplify this, well, with one particular example. Now, of course, all of these people, they work on specific problems, and then they publish nice papers, as you see. And I would simply like to go into one of these papers in order to tell you my thoughts about what our current research is and what our future research might be. So let's zoom into this paper. This is by Maria Troppens and Santiago Rigamonti. Actually, it's not a science talk, so I'm not going to talk about the physics behind you, or not in detail, but I would like to use this example and tell you 1 minute what the science is about here. Right? So what you see here is a class rate compound. And this is a material that is very promising for thermoelectrics. So it has very, very nice thermoelectric properties. So it consists of cages of, let's say in this case it's silicon, could also be germanium or other atoms, but we do it for silicon, right? So we have cages of silicon atoms, and then silicon is semiconductor, and also this structure is semiconducting. But it's not a good thermoelectric because, well, what you want for thermoelectricity is you would like to have a high electric conductivity, but at the same time you would like to have a low thermal conductivity, right? So the thermal conductivity obviously is not good enough in this material. So in order to keep it low, people put, or our experimental friends, they put some heavy atoms in here. They call these rattlers, like for instance barium or strontium, that help minimizing the thermal conductivity. Right? But at the same time, this barium and strontium, you know, these are ions, and these ions, they donate electrons. And donating electrons to the cage means that they make this cage metallic. And this is what we don't want for thermoelectricity, because in a thermoelectric device, you would like to combine a p-doped and an n-doped semiconductor. So what to do about it? Well, in order to compensate for this additional charge, we replace some of these atoms, some of these silicons, by aluminum. So this aluminum, if you fill in enough of these aluminum atoms, and this is, you see here in the z-axis, this is the aluminum concentration, then you would see that this material is indeed semiconductors in the what we call the single phase, or the fully charged compensated cell phase. And you see this if you look at this picture here. So you see that there's no density of states at the Fermi level, so the green line here. However, and this is very interesting because thermoelectric materials have to operate over a large temperature gradient. You see, if you go up the y-axis here, that if you go to other configurations, so other mixtures of these silicon and aluminum atoms, then you may end up with configurations that are not too high in energy, that are not semiconductor but metallic, and this is what you see here with this orange line. So bottom line is, this material may be a good thermoelectric, but maybe not, because at higher temperatures there may be some insulator or semiconductor to metal transitions that would make this material not so good for applications. So we don't know. Anyway, I would like to take this example. So first of all, to discuss how efficient research is, but then also to explain you what the data structure is that we create, or the data that we create behind this. So let's go to the first aspect first. And this is the question, what do we find in the publication? And I stay with this paper and say, okay, maybe a table, yeah? So we publish a table, don't read it, it's just to tell you that we published the table, right? So then a figure, yes, we have several figures in this paper, for instance, showing the density of states of this material. Structure, yes, this is the class rate structure that you have seen. Maybe we also extracted a few other numbers in this paper, but in essence, at the end of the day, we have to admit that we never ever provide all the information in the publication about the knowledge that we have gained over the, I don't know, months, or in this case, probably even years, that we have studied this material in very detail. So there's a lot of knowledge that is lost, that we could use or reuse. because of course nobody wants to read papers that are 100 pages long, so we have to extract the essence. But we also have to accept that a lot of knowledge is lost in our way we're doing research. So don't get me wrong, I really love this way of doing research and to talk to my students and postdocs and work with them on a daily basis. But this way of doing research is in view of the challenges ahead of us, to find better materials and to find novel materials and to solve a few problems of our environment and planet. In view of this, I think it's a very slow process. So we could do better, and I think the Materials Genome Initiative of Barack Obama also is one way of trying to accelerate research, and I think we're going in similar directions right now. So, second question, also related to this paper, is the question: what are the data that we generate, right? So it's said already that thermoelectrics need to, or devices need to operate over a very large temperature gradient, because thermoelectricity means that we would like to recover waste heat and transform it into electricity. And waste heat appears in all kinds of machines and at very high temperatures or different temperatures, and we would like to exploit, so to say, any temperature gradient. So whatever calculation we do, this means we have to do it for a large range of temperatures. So what is this? We need to know the geometry of the material, the phonon spectra, because we want to compute thermal conductivity, we want to compute electrical conductivity, because at the end, the thermoelectric figure of merit, and this is simply one number that we get out here, is more or less the ratio of these two. Right? So method-wise, if you look into this column here, that means, well, we start with a very small input, but then we use density functional theory, for instance, getting the ground state properties. We use many-body perturbation theory, or probably even better, density functional, for the excited state, density functional perturbation theory, or molecular dynamics for getting all the information about vibration and thermal conductivity. And they have seen that we not only use all our methodology that we have in hand, but if you look at the right side now, you see how much of the data that we create. So we start with this very small input of a few kilobytes, but then DFT, in particular molecular dynamics, if you store all the trajectory, let's say, over a large temperature or pressure range, we may end up creating just terabytes of data from the ground state or from the molecular dynamics. The same is true for excited states, where we have, let's say, these non-local operators, for instance, if you want to compute excitation spectra, which not only scale horribly in terms of computation time, but also create a lot of tons of data. And the same for molecular dynamics, for the thermal conductivity. But at the end of the day, so to say, from all these gigabytes and terabytes that we run, or that we produce running our calculations, at the end we get one number out, and this number is basically the output of maybe years long of research and millions of CPU hours that we spend. So throwing all this away basically means a waste of time, a waste of personal power, a waste of energy, because also our computers produce a lot of waste heat, if you like, and of course also waste of computing power, because the next person would basically repeat the same and the same calculation again and again. So reharvesting and keeping data alive is, I think, a big issue that we shouldn't forget. So not to forget also about a lot of high throughput initiatives nowadays. So there are many groups, they produce, don't know, tons of data, but just looking into very different materials, asking the question whether they would be good enough for a certain property. So for a certain device. So for instance, As I said, for thermoelectricity, this would be property 1 would be a good Seebeck coefficient. Property 2 would be probably a good electrical conductivity. Property 3 would be bad thermal conductivity, and so forth. So depending, if you look into solar cells or whatever, you want the material to fulfill certain properties. And then if you do high throughput screening by just checking thousands or hundred thousands of materials, you probably would find 1 or 2 or 3 that fulfill all the criteria, and then there would be many, many others that you simply throw away. So these 3 may be gold, or like a gold mine, and the rest is basically forgotten. And maybe you have spent also 100 million CPU hours on doing such a thing. I'll get back to this. So let's at the moment close the lid of the waste basket and continue. Now, using data, and obviously this is what the aim of my talk is about, is for getting the big picture comes with a few requirements. And the most important requirement, I think, is to have a fair data infrastructure. Because without data infrastructures, we wouldn't be able to harvest all the knowledge that is in there. So what does fair mean? I walk you through this in a second, and would like to show an example what these figures means in terms of material science. Like to mention this paper by Wilkinson, and there's a lot of core authors included, that appeared in 2016, which came up with this abbreviation FAIR. Well, actually means findable, accessible, interoperable, and reusable, not reusable. So, what does findable mean in our terms? Well, findable simply means that we need to store the data somewhere in order to make them useful again whenever you need them. And this was the, let's say, the birth of the Nomad repository. Nomad stands for Novel Materials Discovery. What we have right now is an data infrastructure where all over the world, people running electronic structure calculations, they just can upload and contribute to this data infrastructure. To a central, we still have a central repository there. And uploading means that they share the data, which, well, 99% of the data are open, or maybe even more. So people share the data to the community, but there's also a benefit to this, because data can get more, let's say, attention, or a paper could even get more attention if you also publish the data along with, and getting also a digital objective identifier for this. So this is a huge database. We have more than 100 million calculations inside. And well, I just mentioned before that this fair data infrastructure, this idea of fair data was established or published in 2016. I like to somehow draw attention to this number here, because in 2014, we went online with this repository, and in some sense, we anticipated these fair data infrastructures. So we were maybe even forerunners of this. So far the F, of course, if people upload data to the repository, you see this arrow goes in both ways. Everyone can download the data, or the open data. We don't touch the closed ones, but all the data, the open data, can be downloaded. In that sense, these data are certainly also accessible. But here I start already questioning the fairness, right? I mean, fairness is very different aspects, and it depends also very much on the audience, so to say, and on the domain, how fair data are. But for me, accessible means that they shouldn't be just machine accessible. So, and this is what the repository is. So you can upload data, you can download data, but if you're honest, these data are all sitting in files, and they're accessible, but they're only accessible to experts. So if you run a DFT calculation, I think it's very useful for you to have an input file that someone else has created. Or it's also useful for my students just to look whether they get the same results that someone else has got, or take an input and run a calculation on top of something else. So for experts, this is pretty much useful, but maybe it's not so useful at the moment for experimentalists or for engineers who want to know what the outcome of these calculations are. So in that sense, we started something on top of the repository, which we call the Nomad Encyclopedia. And that means it's what we call a materials-oriented look on the data. That means you search for a material, either by element or by the properties or whatever. Like for instance, you choose all the materials consisting of iron and oxygen or so. Then you get a list of materials that fulfill your criteria. Well, as I said, you have very different search criteria. Then you get a list of all these materials, you may choose one, and then this engine, this graphical user interface shows you what the material is about in terms of structure, or what the band structure is, or what the density of state is, or here we have another material. And people have computed phonon spectra and specific heat and free energies and so on. So the idea is whatever people contribute to this database should be human accessible in the sense that we want to display the results of all this research that has been done. So, and maybe look at data even from a perspective that the creator of the data has not done so far. So this you may, I think, consider a service to the community, because you can call it a picture book if you like. It's a picture book of materials, which I like actually. But I also want to emphasize that there is a lot of scientific questions that you also can answer with having such a tool in hand. And this way I'd like to introduce you a little bit to the work of Martin Kuban, one of my PhD students, who is dealing with similarity of materials. So finally, we want to know how similar materials are, either in the property or in structure, or whatever property you think of. And so he looks into the similarity of density of states, and this is actually implemented, so it's part of the encyclopedia right now. So for every material, for a given material, you can somehow compare any other with it, and you can define a similarity coefficient, which is between 0 and 1. So 0 means completely different, and 1 means probably identical or nearly identical. And so we follow a work here by SIF, but we have further developed it. And just to give you a snapshot of an example, for instance, you're wondering what gallium arsenide, or what the neighbors of gallium arsenide are in terms of similarity in transitive states. So next to it is gallium phosphide, so you see it shares most of the features here. This is something you probably would have anticipated coming from semiconductor physics. There may be other materials that are very similar you would never have thought about, because you don't see these results next to each other. In that sense, I think this similarity search is very useful because you can exploit the same framework, and that's what we're doing right now, is also to explore how similar results of different methodologies could be, or how similar results or dissimilar results between different approximation computer codes and so that can be. So you can use this kind of framework in order to support research questions, actually. So this is based on a few 100,000 materials downloaded from the API and explored, and we show now in the encyclopedia, I think, the 5 topmost similar materials to every material that we have. So let me proceed to the I, which is interoperability. And to tell you the truth, I think this is the most critical figure of this fair. And I start with an example. Now, you see, or this is what I've shown before, that people from all over the world can upload their data. So whoever runs an electronic structure calculation can contribute. So, but it's needless to say that people use many different tools for doing so. So at the moment, we support 40 different codes, which means that for every code, the data are, or the output files are parsed, such that we can extract the information that is there. And from this figure, you see, for instance, the topmost entries in the database. So what is needed in order to do so, to make data interoperable and to make them comparable? So what I said before, in the encyclopedia, you also have this data from different codes, and so how can we really claim that these data are comparable, and even further, if you want to do science with them, whether you can use them on the same footing. So first of all, I mean, we never wanted to convince a code developer to stick to standards that we create. So what we did is that we wrote the 40, or the Nomad project wrote these 40 parsers in order to let the user not bother about whether the results come in kilocalories per mole or Rydberg or electron volt or whatever, right? So the parsers should take care of this. And for this, the metadata are most crucially important, because in order to compare results from all these codes, we need to make sure that we understand what the code contains, or what the output files contains. It means that every single bit of an output file needs to be described, and for this we need the corresponding metadata. Otherwise, you never understand why the energy zero of a VASP calculation is different to the one of GPO, or things like that. So metadata crucially important, and only having this, we could normalize the data such, at the moment at least, what we call the Nomad Archive contains the same data like the repository, but now in the same unified file format, having the same units, such that it really can operate on the large data space. But anyway, needless to say, this is only the first step. So formats and units it took very long. So this was probably the work of 20 person years or so. So to get there, but still it's only the first step if you think about other problems. And if I have time, I talk a little bit about this at the end. So then we come back to the last digit or figure of the R, and this is reusability. And for this, I would like to come back to two issues that I have addressed. One is the high throughput screening. So I said already, probably out of few 10,000 materials, only 3 are fulfilling the criteria that you have imposed. However, this doesn't mean that all the other materials are useless, because they could be used for something completely different. They don't fulfill these properties, but they may fulfill something completely different. So it may not be useful for thermoelectrics, but may be useful for solar cell or whatever. So in that sense, reusable means repurposable. You would like to use data for a different purpose they were originally produced for, and it also is synonymous to recyclable somehow. So open the lid of this basket and just use the information that people have created by running all these calculations. So let's go to the waste basket, but also go back to our time travel, because what we've seen so far, the first 3 paradigms, this is what our nowadays research is about. But I think in the future, there will be a 4th one. And this 4th one is what we call big data-driven science. And it will deal with detection of patterns and analysis in big data. So with things that you would never be able to see from individual calculations or papers. And it would also work with different methods. So not with experimental techniques, not with classical laws, not necessarily, but also with, let's say, computer simulations, but not with this kind of simulations. But we will use tools of machine learning, of artificial intelligence, which is the bit broader aspect. Of course, this hasn't been invented for material science, and so it was first mentioned by Jim Gray in 2007, who worked for Microsoft, so he was not a material scientist at all. but he anticipated that this type of research would be very important for the future. But of course, it doesn't stop at the doors of material science and will also be very important for our own future research. So in that sense, harvesting data, which is a prerequisite, is a very, very important thing. Now coming back to all the applications that we have seen in the very beginning, what we are dreaming of, and this is really a vision, and this will not come in the next 2 or 3 or 5 years, it will take a while, but I think it should be doable, namely to come up with schemes that tell us, or with maps, like a map of Europe, where we look at it and then you know where people would live that speak German or speak English, right? So we would like to have a map in hand that tells us where do I find superconductors in the space of materials, where do I find good materials for photovoltaics or so. Of course, it won't be a two-dimensional map, right? So it depends very much on the descriptors. So what are the actuators, the parameters behind a certain function? And it will be a highly dimensional map, but at the end, I think it should be possible to do so. Now, to give you just a quick glance of a two-dimensional example, our role model, so to say, is the periodic table of elements, which is, I think, truly amazing. So if you think about that, Mendeleev lived at a time where we didn't have quantum mechanics, but quantum mechanics is the essence of any atom, of any property of all the atoms. So it was quite genius to arrange them in a way such that we can read out from this table basically all the chemistry and a lot of physics by just looking at this. And it's also amazing to see that you can do things even without the full knowledge behind. So in that sense, this is, so to say, a role model for us, but of course materials are much more complicated than atoms. So getting back to this fourth paradigm, so first I would like to ask the question whether we are not already there, right? So everyone is doing machine learning nowadays, so there are many, many areas of research where data analytics, machine learning, artificial intelligence, method, you name it, are created. For instance, in chemistry, this is an old field. It's more than 100 years old by now, right? So there's bioinformatics, there's robotics, of course, computer science driving force. A lot of this research is driven by social media. And just think about shopping lists, Google and Amazon and this kind of things. So, however, what I'm claiming, and I'll get back to this in my probably last slide in a few minutes, that we cannot take all these methods from the shelf. So even if there are plenty of them, so it's just a little selection. So there are trees and forests, and there's this regression methods, and there are knowledge graphs. So it's extremely difficult to take a method from the shelf and just apply it to materials data, because material science is so complicated, so complex. As I said, how many calculations do you have to run in order to get one number out? So there are many different theories, many different algorithms behind. So it's not straightforward to just predict something by taking a very, very simple tool from the shelf. Nevertheless, I would like to show you one example from compressed sensing, how we think that we can go along, and which turned out quite successful in the last year. So it's a paper that we published 3 years ago. There's a lot of more work done in the meantime, particularly also in Matthias Scheffler's group. I still like this example because it's so simple, and that's why I would like to share it in, I don't know, 2 minutes with you. So suppose you give me 2 atoms, call them A and B, and these atoms should be, well, they form an octet, so they should have in total 8 valence electrons together, right? So then I tell you whether this material will crystallize in rock salt or zinc blende. So this is a very old problem. We call it the Philip Fanfiction problem because these two people started to look into this problem in the late 60s already, and there have been many people working on them. So it's a whole list of references. But I take it as an example for the methodology that we developed. So for simply, this is now the role of descriptors, so to say how to arrange these materials in order to find a separation line between these two, how to tell them apart from each other. And we use compressed sensing for this. I just show you the result here. So you, if you're interested in, you can look at the descriptors. They actually are meaningful quantities in order to interpret what you may call a formula or not. But it's very interesting. So everything, what you see here in the color code is the total energy difference between rock salt and zinc blende. So whatever is in blue is in favor of rock salt, whatever is in red is in favor of zinc blende, and whatever is green, here the total energy difference is so small that the material hardly can decide what it wants to be. So with these descriptors that we found by compressed sensing, we obviously are able to not only qualitatively but also quantitatively tell what kind of crystal structure they would like to have. Now, what do we put in as an input here? Just the properties of single neutral atoms, nothing more than this. So there's no information going in from the crystal structures themselves and the structure properties. So it's just predictions from neutral atoms. We use compressed sensing with this, and if you're interested to play with this, actually, you can find this example in the Nomad Analytics toolkit, where you can play with different descriptors and then see whether you get the same results and how far you are from these results if you choose something different. Now, in the very last minutes, I just tell you how we do. So as said, we start with what we call primary features, which are just atomic quantities, like distribution of the S&P like orbitals or electron affinity, ionization potential, band gaps, this kind of things coming from atoms. But then we combine these features non-linearly by adding, subtracting, multiplying, taking the root, exponential, and so on of these features. And this way we can create 10,000s or 100,000s or millions or trillions of features. And then we try to learn a linear relationship between the property and the descriptor. So this way we have a huge descriptor space. We know the properties and we try to find the relation between this. And we can do so by finding a linear relation because we put all the nonlinearities into these mathematical operations here. And so, in other words, from our test set of materials, we try to minimize the distance between the predicted and the computed quantities. And the way compressed sensing comes in here is that we apply them as a penalty, the L1 norm. Now, as I said, we're working further on this, but I just wanted to tell you the simplest example. Now, the question you still can ask, is this just a hype using machine learning or artificial intelligence for material science, or can we really revolutionize this field? I think we can start a revolution, but we need to be very careful because we are not yet there. And yes, as I said, I think the future, or once a future type of research will be to find trends and patterns, but there's a big but. The but is that we also need new and novel developments. And first of all, we need novel tools because, as pointed out before, whatever Amazon develops for, trying to convince you that if you have shoe number 42, that you also need a blue shirt, is very different from material science. So we really need something that's informed by the domain. Yes, we need big data for this. That's why we need also the data infrastructures, but we also need the right data for this. And the right data means that if you just create more and more data, and we look for the needle in the haystack, creating more data could just create more hay, but we want to find the needle, right? So in essence, we would like to find outliers because they're most precious, and not those outliers which are coming from wrong calculation, but outliers because they're really something new. And in that sense, we should not stay within a box, so not only search for superconductors within the family of superconductors, but reuse data or repurpose data by looking into other families of data to find for outliers there they may be useful for something else. And in particular, and that's why I come back to the novel tools, so if you want to do interpolation, I think that's fine. So if you want to stay within a family, then probably you can use quite a lot of tools that are already there. But if you want to predict something that's really new and novel, you need to go beyond interpolation and give all these tools as much predictive power as possible. So with this, I'm more or less done. I just want to introduce you to the next steps that we are doing. And for this, well, we have been doing time travel, so I go back in time again. Mentioned probably that we established this repository. I made it public in 2014 already, and this was a bilateral project between Matthias Scheffler and myself. It started actually from a project in thermoelectrics, a bilateral project where we found it's very useful, not only for our groups, but probably also for others, to be able to host the data, to share the data, to organize the data, and also make use of it in a later stage. Out of this became a very big European Center of Excellence, where we had 13 partners, I think. So there were 8 complementary scientific groups, also 4 high-performance computer centers that are indicated here. And so this was funded until 2019. And after this, we started a next step by founding an association. So this is FAIR-DI is an association according to German law, Fair Data Infrastructure for Physics, Chemistry, Material Science, and Astronomy. And the idea was not to stick only with computational material science, which is one of these pillars here, but also expand towards experiment, towards soft matter, towards different functional materials like catalysis and so on. So there's even astronomers on board where we share the data processing and all kinds of data aspects. Well, meanwhile, we also implementation network of FAIR, which is the realization or part of the realization of the European Science Cloud. And out of this FAIR-DI, there was a consortium coming out. So if you look at the condensed matter pillars of this association of FAIR-DI here, so if you leave out astronomy, if you like, and put together not only computational science, but also experiment and synthesis, and of course the infrastructure that we need. So we established a consortium that's running now for the National German Research Data Infrastructure. And I would like to stop after showing you one more transparency, just to give you one example how we think or what we think about to integrate experiment. And then we also see that whatever I've shown you right now, I told you this was a hell lot of work. So many, well, several 10-person years entering into this. If you look into experimental science and also synthesis, the problems there are much more complicated even. So just one example. This is optical spectra of samples that people call silver. Right? So, and if you look into this, I mean, you wouldn't expect that this is one material or one material that's reproducible. So this shows you already the veracity of results. So you have different sources, you have different sample quality, you have different experimental quality. So in order to make data interoperable there, you have to do a hell lot of work. But also deals or comes with variety, and variety means that there's many different methods how to can obtain the optical spectra. So you can more or less directly, but not completely, getting from ellipsometry. You can get it from absorption, from reflectance spectroscopy. You can even use electron spectroscopy for this. So you need to know when processing the data into one quantity that all of them have in common, what are the processing steps, and what are the bottlenecks and the uncertainties behind doing so. And of course, you can also get this from different levels of theory. So interoperability, as I said, is a huge problem, but I think in a concerted effort, and in particular having the community on board, it's doable to establish the data infrastructure that is useful for the community. Our own last recent steps was talking about Nomad. Markus Scheidken has completely refurbished our infrastructure, so now we have unified software for repository and archive, also extending now to Encyclopedia and Analytics Throughput. We have improved functionality, and we are prepared for extension towards experiment, even having already a few prototypes available where we have shown how it works, and yeah, that it works. Yeah, with this, I would like to thank you for your attention, and happy to answer any question.
Okay. Thanks a lot for this very instructive overview, which gives many important information for us. I have recorded this talk to make the information also reusable for our thinking and our future research in connection to this big data structure. Thank you a lot.
Thank you.
The talk is open for questions, and I would like to ask Tim to take the discussion over.
Okay, yeah. Thanks, first of all, also from my side to Claudia. I have a few questions on the list, but I think because this is RTG seminar, I don't know, maybe students first. So are there any questions from the students or whoever would like to ask? Otherwise I start. Then I start. So